Okay, so to summarize, remember that a galvanic cell is one in which electricity is generated spontaneously. And in a galvanic cell, that means the anode is the site of oxidation. I used to remember vowel with vowel. And the cathode is the site of reduction, consonant with consonant. Remember, oxidation is lost, so the anode is where the electrons are lost, and the cathode is where they are gained. Because the anode is the site where the electrons are lost, as that atom loses electrons, it becomes positive. So as more electrons are lost, there's more positive charge that's building up in solution. On the cathode side, because the electrons are being gained by positive ions, then there's going to be a buildup of negative charge in solution, because as those positive ions leave the solution, it leaves the spectator negative ions in solution. Your anode is going to get smaller. The piece of metal will get smaller over time because the metal ions are leaving and they are becoming positively charged and joining the solution as they lose electrons. The cathode is getting larger over time because as the ions in the solution, the positive ions gain electrons, they become neutral and then they join the metal bar, so it gets larger. In the salt bridge, because it's a buildup of positive charge, the anions in the salt bridge go towards the anode to try to counteract that positive charge buildup. And in the cathode, the cations are attracted to the cathode because they're trying to counteract the buildup of negative charge in the solution. They are attracted to that negative. So it's nice and easy. Anodes attract anions and cathodes attract cations. Now, I told you it's not just enough to know how the cell works. You have to actually calculate the cell potential. The cell potential is going to be the voltage that you produce as a result of putting the two anode and cathode together. It's called the driving force of the electrons, and it's calculated between the difference between the two electrodes. We call cell potential E cell, and if it's standard cell potential, we write E naught cell. The standard part means it has to be at 25 degrees Celsius, the pressure has to be 1 atmosphere, and any aqueous solution has to be 1 molar. If these conditions are not met, then the cell potential will change, and we'll talk about that by the end of this chapter. Like I said, the cell potential is measured in volts, so a lot of times instead of calling it cell potential, they'll call it cell voltage. And if you calculate it, and your E cell is positive, this is huge. If you get a positive E cell, then the reaction is spontaneous. So remember, if you think back to a couple chapters ago, when delta G, which is the ultimate predictor of spontaneity, when delta G was less than 1, then it was, less than 0, it was spontaneous. And when K was greater than 1, because you made a lot of products, then it was also spontaneous. Now add that to this, you now know that when E cell is greater than 0, then you have a positive spontaneous reaction. Now, this is how you're going to calculate the cell potential. It's a very simple formula. It's going to be the cell potential is equal to the reduction potential plus the oxidation potential. Now, as simple as this formula is, it really confuses students. Now, let's talk about where these cell potentials come from, and then we'll talk more about how to use the equation. Cell potentials are kind of complicated to measure initially because you have to have something losing electrons and something gaining electrons in order to measure the cell potential. The problem is that if you don't pick a constant to measure all of the cell potentials against, then you don't know what part of the potential was the anode's responsibility and what part was the cathode's responsibility. So, what they decided to do was measure the potential of single electrodes against the She. And they call it the She because it stands for standard hydrogen electrode. So they chose this electrode that's represented by the following equation. 2 H pluses plus 2 electrons produces hydrogen gas. And they said, all right, let's set this one to 0 volts. We'll say that this one has no cell potential. And then we'll measure all of the other ones against this one to see what happens. So what happened is if they measured it against hydrogen and it came out negative, then if it came out negative, they knew it didn't want to undergo oxidation. Now, how do I know that? Because this particular potential is a reduction of potential. And I know that because the electrons are on the left, they're being gained. So that's a reduction potential, and if the one that they hooked up to it came out negative, that means it didn't want to undergo oxidation, it wanted to undergo reduction. So basically what they did is they hooked everything up to the She, and then they figured out what numbers they got. Now when they report them though today, they report them all as reduction potentials. Now, again, the reduction means that the electrons are gained, so they're all on the left side of the equation. If it was an oxidation potential, you would have this plus this or whatever. It may only be one reactant, but regardless, you'd have the electrons on the right. So keep in mind, reduction reactions are gaining electrons, so the electrons are on the left. And then oxidation potentials have the electrons on the right. I don't know my sides, right side, because they're losing them. So remember that they're all going to be reported as reduction potentials. So when I give you an appendix values, they're all going to look like this. The electrons will all be on the left. If the value on the chart is reported as a positive reduction potential, that means it's spontaneous for reduction. So it wants to undergo reduction. If it's negative on the list, that means it doesn't want to undergo reduction. Instead, it would rather undergo oxidation. So here is the table of standard reduction potentials. And like I said, if you notice in the middle, okay, in the very middle of the table is the She. It's the basis of everything else, and it's listed as 0 volts. Anything above the She has a positive reduction potential. That means it really wants to undergo reduction. Obviously, the top one's more likely to undergo reduction than the bottom ones. Down here, they really want to undergo oxidation. So they are strong reducing agents because they want to undergo oxidation. And these are strong oxidizing agents because they want to undergo reduction at the top. Now, we're going to use those half reaction potentials, all those reduction potentials, to calculate the potential we would get if we had a cell, an anode and a cathode. Now, the most important step is to first decide which electrode is your anode and which one is your cathode. Now, depending on the particular reaction, there's 3 ways to do this. 1, you must match a reaction if they give it to you. So if they're asking you if the particular reaction would produce a positive or negative cell potential, you have to match that reaction. No matter what the cell potentials say, in terms of likelihood of undergoing reduction or oxidation, you have to match the reaction they give you. If there's no reaction given, second case, and the cell is galvanic, you know that galvanic means spontaneous. So whatever one is most positive on that cell potential list is the one that will do reduction, and you'll leave it the way it is. But the other one on there that's less positive, it may even be negative, will have to be flipped because it's less likely to undergo reduction than the other one. And so we'll flip the reaction, flip the sign of the value on the chart, and that will be our oxidation reaction. If there's no reaction given again, but the cell is electrolytic, which means it's not supposed to happen, then the one that's more negative will remain the way it is, and you'll flip the one that's more positive to become oxidation, because we don't want the cell to go overall. You will use the half reactions from your standard reduction potential. It's even provided on the AP exam. And then you will simply add up the 2 values to figure out your cell potential in volts. Your units will be volts. So here's an example of a cell, and it says calculate the cell potential for the cell diagrammed to the right. Now the first thing you have to do is analyze the picture. Now they don't tell you which one's the anode and which one's the cathode, so you have to figure it out. And there's a couple hints here. One of the hints is the direction the electrons are going. So you can notice that the electrons are going this way. And remember, the anode is where they lose electrons, and the cathode is where they gain electrons. So the fact that the copper is gaining electrons tells me this is the cathode, and the fact that the zinc is losing them tells me this is the anode. Remember, the cathode is the site of reduction, and the anode is the site of oxidation. Other ways you could have told. You can look at the salt bridge. You can see here that the cations are going towards the cathode and the anions are going towards the anode. You can also look at the pictures down here and you'll see that the copper is gaining electrons to become copper solid, or that the zinc is losing electrons to become zinc 2+. So there's a lot of different ways you can look at it, but regardless, you have to figure out which one is the cathode and which one is the anode. Now, once you know which one's the cathode and which one's the anode, you have to look up the cell potentials on the chart. Now, remember, the chart is listed in terms of reduction. So I can find this one's half reaction from the chart. And if you look, you'll see copper 2+ plus 2 electrons becomes copper solid. And if you reference that chart in your notes, you'll notice that its cell potential for reduction is listed at 0.34 volts. Now, we have to find a potential for the other one. However, just remember that whatever you find on the list is going to be the opposite of what we want here, because this is oxidation. According to the picture, I can see that the zinc solid is becoming zinc 2+ plus 2 electrons. Now remember, I won't find it this way on the chart. On the chart, I'll find it the complete opposite of this, because this is oxidation. And on the chart, it will be written as reduction. So what you do is you look up zinc 2+ plus 2 electrons makes zinc solid. And on the chart, it's towards the bottom, and it says negative 0.76 volts. But we're going to do the opposite of that. And we're going to write positive 0.76 volts. Now the last thing we have to do is calculate the overall cell potential by taking the reduction of 0.34 and adding to it the oxidation of 0.76. And then just remember you're adding. So it's least decimals. These each have 2 decimal places. So it's going to be 1.10 volts. And then here's my question. Would this cell proceed spontaneously as written or not? Since you get a positive cell potential, it is spontaneous, meaning it will go on its own as the way it's drawn. Now, if you don't have a picture, okay, read the question carefully. First, the second word is important. It says it is a voltaic cell. Remember, voltaic means another word for galvanic, which means it's spontaneous. So when I'm done, my E cell, it has to be positive. If it's not, then I screwed up. It said it's to be designed at standard state conditions using the following half reactions. What's the potential? I have to make this positive. My overall, once they're done adding, has to be positive. First, I'm going to look up their reduction potentials. Right now, if you look, these are both written as reduction. I can't have 2 reductions. I have to have 1 oxidation and 1 reduction. So one of these is going to have to flip. The other thing they tell you here is this potential of the second one is negative 0.91 because it's not on our list. The manganese is on your list. If you use the reference chart that you have, the appendix values, in your notes you'll find that Mn2 plus 2 electrons makes Mn solid is negative 1.18 volts. Now, they're both negative. But remember, the one that's more positive, or less negative, whatever way you want to say it, will stay the way it is because it's more likely to undergo reduction than the other one. So since this one is more positive, it will stay the reduction. I'm copying it down. It's going to be my reduction, and it's going to be negative 0.91. And then the other one I'm going to flip. So I'm going to have Mn solid becomes Mn2 plus 2 electron. And its oxidation now, since I flipped it, is 1.18 volts. And then I'm going to add them up. So cross off the electrons. My overall reaction, if asked, would be Cr2 plus Mn solid makes Cr solid plus Mn2 plus. If asked, you're not right now, but if asked. And then I add up negative 0.91 plus 1.18 volts, and I get E naught cell, is 0.27 volts. And then I'm done. Here's another one. Now, in this case, determine if the following reaction is spontaneous or not. You don't have a choice. You don't get to decide which one you're going to leave alone. You have to match this reaction. If they give you a reaction, you have to match it. So my suggestion is that you split it into two half reactions. So Fe2 plus becomes Fe solid, and Sn solid becomes Sn2 plus. And then add the electrons because the elements are fine. There's no oxygen, there's no hydrogen, eating old hibachi chicken. So I'm going to add 2 electrons here, add 2 electrons here. These are the two half reactions. I have to find their potentials. And I can tell you right now, one of them is reduction, one of them is oxidation. So which one shows the reactants gaining electrons? This one. This is my reduction. This one is my oxidation. I will find the first one's potential on the chart exactly as written because the chart is all reduction. If you look, you'll get negative 0.44. This one, I'm not going to find that way. On the chart, I'm going to find it the opposite. I'm going to find Sn2 plus 2 electrons makes Sn solid. And when I find that value, which is negative 0.14 on the chart, I'm going to flip it to become positive 0.14 here. I add up the two values and I get that E naught cell is negative 0.30 volts. What does that tell me? Is it spontaneous or not? Since it's a negative answer, it is non-spontaneous. Here's another one. Determine if the reaction is spontaneous or not. You have to match this reaction. So split it. Fe3 plus goes to Fe2 plus, and copper goes to copper 2 plus. Now, there's no elements, there's no oxygen to balance, there's no hydrogen, so just charge. I got to put an electron here, and I got to put 2 electrons here. Now, if I was still doing eating old hibachi chicken cold sucks, before I added them up, I would have to multiply this reaction by 2 because I would need these electrons to cancel. What screws students up is when they go to look up the actual potentials off that reduction thing. Because what you're going to find on that potential chart is you're going to find Fe3 plus 1 electron makes Fe2 plus. And the value that's on the chart is negative 0.77 volts. What students mistakenly do is they times the potential on the chart by 2 because of these 2's. Do not do that. Do not multiply the standard potentials by the coefficients. They are unaffected. In the end, this one is its reduction potential is still negative 0.77 volts. This other one I'm not going to find. This is my oxidation, so I have to look for the opposite of this on that chart. And the opposite of this on the chart is going to be negative 0.34 because on the chart it's positive 0.34. When I add them up, I get 0.43 volts. Now, because E naught cell is 0.43 volts and it's a positive answer, I know that the cell is spontaneous. Now here is a huge, important conceptual question. If you can truck along with me on this, then it tells me that you're truly understanding what's going on so far. Okay, you have 1 molar solutions of iron 2 nitrate and silver nitrate, along with iron and silver electrodes to construct a voltaic cell. It has to be voltaic, which means it has to have a positive E0 cell. The salt bridge has sodium nitrate. Complete the picture on the slide given by doing the following: writing the symbols of the elements and ions in the appropriate areas on the solutions and the electrodes, which are the metals. Identify the anode and the cathode. Indicate the direction of the electron flow. Indicate the cell potential. Write the appropriate half reaction under every container. Indicate the direction of the ions flowing in the salt bridge, and indicate the species that's undergoing oxidation and reduction, and write the balanced overall reaction. This is a lot, but if you can do this, you truly understand what's going on. So here's what I know. Okay, you kind of take an inventory. My solutions for my beakers. Here's what I got. I have, that's supposed to be a K, it's terrible. I have iron 2 nitrate, and I have silver nitrate. Now remember, when they break up, because they're solutions, they're going to break up into their ions. This is going to give me Fe2 plus and NO3 minus. And not just NO3 minus, but 2 of them every time it breaks up. This is going to give me silver plus and NO3 minus. Okay? Now, metals. What metals do I have for my electrodes? I have iron and I have silver. And I'm noticing something. What I'm noticing is I have iron 2 plus and I have iron. I have silver plus and I have silver. That's going to be my half reactions. Now the last thing that I know is I have for my salt bridge, I have NaNO3, which remember will split into Na plus and NO3 minus. Now, if I look, knowing that I have Fe2 plus and Fe, and I have silver plus and silver, if I go look at my reduction potential list, okay, I will find a couple things. I will first find that Fe2 plus 2 electrons on the chart makes Fe solid. And it does that with a potential of, I gotta find it, negative 0.44 volts. Then the silver plus E minus makes Ag. On the list, the silver plus has a potential of 0.80 volts. When I look at these two potentials, I immediately know which one is which. Remember that they're all written as reduction potentials. So the one that's more positive, which in this case is the second one, that one is going to be my reduction. So this is my reduction. What does that mean? I have to take the other one and flip it to make it my oxidation. Now, where you put them on the actual picture is irrelevant. You can put the anode on the left, you can put the cathode on the right, you can put the cathode on the left and the anode on the right. It doesn't matter. Here's what I'm going to do. I'm going to make the left side the side for the iron. But when I write it down, remember, if this is the iron bar, this will be the silver bar. Okay? This will be the iron nitrate solution, so I'll have Fe2 plus, and remember, I get 2 nitrates, and I want to show it accurately. In the other one, I'll get silver plus and NO3 minus. What will happen in the beaker on the left? The opposite of what I thought originally. The iron will become iron 2 plus 2 electrons. On the right, the silver plus an electron will become silver solid. This is now, because this is the one on the left is the site of oxidation, this is now my anode. On the right, because it's the site of reduction, this is now my cathode. Also remember that the electrons are flowing from the anode to the cathode. So I know that my electrons are going this way. I'm going to erase some of this. Because at the anode they lose electrons, and at the cathode they gain the electrons. I also know that in the salt bridge I have a solution of sodium nitrate. Sodium nitrate is made up of Na plus and NO3 minus. Remember, Na plus is a cation, and cations go towards the cathode. So the Na plus goes this way, and the NO3 minus, the anions, go towards the anode. Now, the last things they want me to do, okay, they want me to actually calculate the cell potentials. So, to calculate the cell potential, remember, this reaction for the anode was going to be positive 0.44 volts because it's the opposite of what was on the sheet. And this one's going to be positive 80 volts. If you take positive 0.44 and you add positive 0.80, you get 1.24 volts. And that's exactly what this voltmeter at the top would read. So in the top, if you want, you can put 1.24 volts in the voltmeter. So let's see, did we do everything? We wrote the symbols of the elements and ions on the solutions and the electrodes. We identified the anode and the cathode. We identified which direction the electrons are flowing. We did the cell potential, it was 1.24 volts. We wrote the half reaction under each container. We indicated the direction the ions are flowing in the salt bridge. We identified what was going to be oxidized and what was going to be reduced. Well, I guess we could do a better job of that. In this case, the Fe solid was oxidized and the Ag plus was reduced. Oh, and then the last step, we have to write the overall balanced reaction. So to write the overall balanced reaction, what we're going to need to do is create a little space here. We're going to take the two reactions that we wrote, Fe solid goes to Fe2 plus 2 electrons, and we're going to add to it Ag plus E minus goes to Ag solid. Now, before I can add these up, I do have to make the number of electrons equal. So I'm going to have to multiply this by 2. Add them up. My overall reaction, I don't want to use red right there. My overall reaction should be Fe solid plus 2 Ag plus, arrow, Fe2 plus 2 Ag solid. And that's it. So remember, this is super important, okay? If we are relating thermodynamics, which is when you learn delta G, to equilibrium, which is when you learn K, to now redox, electrochemistry, which is when you learn E cell, this is how they're all related. If a reaction is spontaneous, E cell is going to be positive, but G will be negative, and K will be greater than 1. If we have a non-spontaneous reaction, E cell will be negative, G will be positive, and K will be less than 1. If it's at equilibrium, E cell is 0, G is also 0, but K is equal to 1. And we're going to go over how to calculate them next.